So the next speaker is, thank you very much, Alexander, again. So next speaker is Samaresh. We'll talk about X-ray spectral timing studies of NGC 7456 ULX1.
Hi there. Do you see my screen?
Yeah.
Okay. Hi, everyone. So I'm Samaresh Mondal, and I'm a fourth-year PhD student in Copernicus Astronomical Center in Warsaw, Poland. And in my PhD, I mostly focused on studying ULXs. So in today's talk, I'll be talking about one particular source, this NGC 7456 ULX1. Yeah, so I wouldn't spend much time on introduction as Matteo already given brief overview. But I would like to add one sentence, like ULXs are mostly observed in the outskirt of the galaxies, like here you see in the figure. And so in the figure you see the HST image, and then the contours from the Chandra is overlaid. And these red circles indicates the sources that have luminosity of 10 to 39 erg per second. And these are like the situated in the outskirt of the galaxy. So yeah, so it's clear that these are these sources cannot be powered by supermassive black holes. Anyway, so let's see about this NGC 7456 ULX1. So here in this figure, you see the time average spectra, and this ULX has similar spectra to other ULXs, and you need pretty much two spectral component. One is this soft component, this BB, and there is another high energy component, this nth com. And these two components usually dominates below and above 1 keV. And so the source is in the soft ULX state, like where the soft component dominates over the hard component. So, and if you look very closely, there is a excess emissions around 6.4 keV, and this is due to iron K alpha emission. And I would like to emphasize here that this is the only second ULX where we find these emissions. And so far, on the iron K alpha line was found in M82X1. So this iron line is really rare in ULXs. As we do not have much signal to noise ratio above 5 keV, so we just had an upper limit of the width of the line, and the width of the line indicates that the line should be originated around 85 Rg. And also the equivalent width of the line is really high, around 2 keV. So then we see the light curve. So in the upper panel, you see the full band 0.3 to 10 keV light curve, where you see the small, very short-term fluctuation due to the Poisson noise, and then you also see the long-term trend. And on the bottom panel, what we did is we smooth the light curve so that the fluctuation due to Poisson noise are eliminated. So in the bottom panel, you see the soft band light curve in 0.3 to 1 keV band and the hard band light curve in 1 to 10 keV band. And you see the long-term trends. And if you see very closely, and you see that there is a slight delay between the peaks of the two bands. So to explore more, we did Fourier timing analysis or Fourier time lag analysis. So we did the Fourier time lag analysis between the soft and hard band, and what we found that the there is a delay between the soft X-ray photon and the hard X-ray photon. And in this figure, you see that the delay is around 1300 seconds. So this lag is really large. So compared to X-ray binaries, but could it be similar to like AGNs, like where in AGN like you see like larger lags, but in that case, like if you consider that the delays is due to the reflection from the primary emission and then the reflection from the disk, and then if you consider that the delays that the reflection happens around 10 Rg, then it would imply a black hole mass of 10 to the 7 solar mass, which is very high. And so like to see like what is happening, so we did the covariance spectra as we saw the coherent spectra from the yesterday's talk from Phil Utley, yesterday's talk, yeah. So the coherent spectra is really powerful tool. So you can you can construct an spectra depending on the time scale you interested, and you can pick the correlated signal between the soft and hard band. So we constructed the coherent spectra. So here in this figure, you see in the gray plot, you see the time average spectra, and in the red point, you see the coherent spectra. And the coherent spectra looks like it has a trend to like it follows the harder component. So which is kind of really strange. So do you have any other source that follows the similar trend? Well, NGC 1313X1 also has a similar trend. The coherent spectra seems to follow the harder spectral component. So I would like suggest you to see this paper, Middleton et al. 2015, where they also computed the coherent spectra of other ULXs. So yeah, so in X-ray binaries, like in the hard state, you also see the contribution from the disk. And this is clearly present in the coherent spectra, but in this case, like this 2 ULX, we do not see that contribution in the coherent spectra from the disk. So what could be the origin then? It could be that the origin is due to the delay between this delay is due to scattering inside the medium. So there is this recent paper came by Luang Trip et al. They also considered this possibility that the harder photon goes through scattering between this wind medium, and that leads to a delay. Here in this figure, you see the soft lag has been discovered so far in the ULXs. So we have like so far 5 ULX that we have this soft X-ray lag. And in this figure, you see in the parentheses the frequency range where this soft lag was observed. And yeah, so in this 4 sources that are sits above on the figure, like they have almost similar amplitude, and they also have been observed like on the similar frequency interval. Whereas this NGC 5408X1, it has very small, I mean, compared to those 4, and the soft lag in NGC 5408X1 was observed at higher frequency interval, like around 5 to 20 hertz, 20 millihertz. So yeah, so it seems like, I mean, we need to discover more and more sources, then we can have an idea like what is going on in these sources and what could be the origin. But it seems pretty much that these 4 sources have same origin or same type of physical processes going on, and it might be that NGC 5408X1 has different origin compared to these 4. So it's pretty much we still don't know like what's going on. And so yeah, so this is the summary. Like we discovered the iron line in NGC 7456 ULX1, and we also discovered the soft X-ray lag with amplitude of 1300 seconds. And we don't know the origin of the soft lag, but it could be that the scattering inside the wind medium. Okay, so thank you for the attention.
Thank you for your talk. Any question? Okay, so